Hello, class 12th physics, circuit-based problems. So mostly I have covered all the questions related to series and parallel combination only. And I have avoided some higher topic like Kirchhoff's law and meter bridge and all that because I'm going to cover those topic in a separate video. But here, um, the most possible circuits as far as class 12th is concerned, I have covered those circuit-based problems here. So starting with very simple, very easy type of problems, which I don't think any student would face any problem to solve, but consider it as a warm-up type of question. So here we have these 5 resistors along a single wire, and if path is single, same path, then they are in series combination. So this is my time consuming method, right? R1, R2, R3, R4 and R5, and then we can write R1 till R5 are in R1 till R5 are in series. So R, we know that the formula is R is R1 plus R2 plus R3 plus R4 plus R5, and okay, so here it is 3 plus 2 plus 2 plus 3 plus 5 equal to 15 kilo ohm. Remember, to increase some technicality, I have introduced kilo ohm. This type of value can be given there. Okay, I didn't mention anything else here, but let us suppose they ask to find current through the circuit, then I equal to V upon R, and V is 100 upon R 15. It is kilo ohm. So actually generally we write 10 to the power 3, that's also okay. So it will be 1 upon 150 ampere, and you can easily divide and find out the current. Okay, next here, so these three capacitors are in series because there is single path. So uh, time consuming part, C1, C2, C3 are in series, and here we have series formula. So just ensure yourself that whether you are applying correct formula or not, because this can be a problem with the student, that they know that for capacitance this formula is used in series. In resistors we directly add them in series, but in capacitor we use in this way, 1 upon type. So remember this thing. So while solving a problem, ensure yourself whether you are applying correct formula or not. So another question, whether we have to convert microfarad into farad. So not required actually. We will report our answer in microfarad. No problem with that. Okay, so it is, I'm directly writing C 10 over 4. It is 2.5 microfarad. And let us suppose if they ask us that how much is the charge stored by the capacitors. So um, all of them are in series, so whatever be the total charge will be the charge in each. As in current, in series combination current remains same in each resistor, so also in capacitor charge remains same in each of the capacitor. So Q equal to CV. C is 2.5, and now if we want, we can convert it into 10 to the power minus 6, or if we are very sure, then 25, but not coulomb but microcoulomb. So ensure yourself. Here I will encourage you to put 10 to the power minus 6 to avoid such type of confusion. And okay, so that's also in series combination, charge remains same, so in each of the capacitor it will be 25 microcoulomb. All right, here we have a series combination of 3 cells. So E1, E2, E3 are in series. Here it is. Generally, when look like here, uh, 10 volt was given, so we haven't put it as EMF of 10 volt. Generally, what is the value of potential difference across a cell is given, we consider it as a potential difference. But when there is internal resistance also given or mentioned in some way, then we will not write V equal to this, but E equal to this value. So in series combination, E net is equal to E1 plus E2 plus E3. Well, we can apply a direct formula also, so no problem with that, but we can go through this way also. 18 volt. And internal resistance, all internal resistances are in series combination, so R1 plus R2 plus R3, so 0.5 plus 0.5 plus 0.5, so 1.5 ohm. So let us suppose, actually I haven't written anything here, but okay, let us suppose I'm asking you to find current and potential difference across this 60 ohm, across this 60 ohm. Okay, so in order to find current, remember this formula which you can never forget. So En Rn. So current will be, actually it is a direct formula also, but if you don't remember that, you can follow this pattern also, or you can directly apply that formula and you can get this current. So 18 upon 60 plus 1.5, which is, I guess, 0. Maybe 0.3 ampere approximately. You can calculate it, but I'm going in a direct way. So V equal to IR. I is 0.03, R is 60. So approximately it is, uh, actually if we divide it, no, so it will be 0.029 something. So I have done it in a tricky way, in a shortcut way. That is why our answer will differ. So you can solve it accurately and then write it in the comment, your correct answer. Okay, now see this. So you can see here how we have connected here. There is a huge gap between two cells. Here they were close to each other, so it doesn't matter. So this conducting wire doesn't matter, because we consider that it has negligible resistance or no resistance. So once again, E1 E2, so E1 E2 are in series, so E equal to E1 plus E2. See, if there are different EMF, then there's no formula for that, so we have to proceed this way only. Equal to 5 volt, and internal resistance R1 plus R2, which is 1 plus 2 equal to 3 ohm. So I will be En upon Rn plus R. So En is 5, Rn is 3, plus R is 5. It is 5 upon 8, 0.62 something ampere. And in order to find EMF across this, okay, last time I did, I go with this formula. This time I will use another formula. Actually, it doesn't matter. If you find it through this way, you will get same answer, and this way still same answer. So E is 5 volt minus I is 0.62 and R is 3. So once again, I'm leaving calculation for you. Okay, next. Again, these are in series combination, but there is a problem. See, in series combination, when you connect cells, what you do? You connect positive of one with the negative of other, like here, positive, negative. This negative, this positive. Okay, this positive to this negative. Now this positive to this negative, but this positive to this positive. It is something like if you have a torch. In our time, this type of torch were there. I would call them Dadaji ka torch. So it required actually 4 cells. Once I did an experiment, uh, and I reversed one of the cell opposite way. I felt that it will not glow now, but still it was less bright then. Earlier it was enough bright, but at that time when I reversed one of the cell, it was very faint. I mean, its only filament was glowing. Well, What happened actually? The reason is subtraction. We know that in series combination of cells, we have to add EMF, but keep this thing in your mind. If cells are connected in this way, that positive of one is connected to positive of other, then we have to subtract. So net EMF will be E1 plus E2 minus E3. It will be minus. So E1 1.5 plus 1.5 minus 1.5. So it is very easy, 1.5. So we have connected 3 cells, but still 2 will be cancelled and 1 remain. It can also be done by taking 3 different cells. No problem. 2 cells which are in proper manner connected. Then we will add them and subtract with that improperly connected cell. Okay, so it is 1.5 volt, and once again, okay, see, but net internal resistance will add up. It has no problem with the polarity plus minus. So internal resistance is internal resistance, no problem with that. So some of the student might subtract the resistance. No, actually it won't be going to happen, because resistance is resistance. It has nothing to do with the polarity. Okay, now we can find I equal to E net upon R net plus R. The E net is 1.5, R net is 1.5 plus, oh sorry, 3 plus 9. So it is 12. It will be 0.125 ampere. And if we require to find potential difference, you know how to find. So I'm moving to next. All right, now parallel combination. So it's quite simple. First I will consume some time by labeling. So I will write R1, R2, R3 are in parallel combination. Okay, so 1 upon R equal to 1 upon 4.5 plus 1 upon 4.5 plus 1 upon 4.5. Oh, 1 upon R, 3 upon 4.5. So R equal to 4.5 upon 3, which is 1.5 ohm. And if we want to find current, so now it is quite easy, V by R. And remember, sometimes it can be asked that find current through each. At that time you can directly do that, because in parallel combination potential difference remains same, so we can directly apply formula. Okay, here again C1 C2 C1 C2 C3 are in parallel. So now we know that in series combination we have this formula. So generally focus on this, whether capacitor is given in parallel or not. If it is given in parallel, then it is very nice to see, because we have directly add them, no need to do anything else. 900 picofarad. Pico, you know, 10 to the power minus 12. So, and if we require to find charge, you can do that now. So I'm not going to do that. So I'm moving ahead now. Parallel combination, so net EMF will be 2 volt. It will remain same for similar cells. If it would not be similar, then we have other method. Then we can't say that EMF remains same. Then we have different method for that. Okay, so but internal resistance, we have to find it. Okay, that is 0.5. I will put it later on. So I equal to En upon Rn plus R. En is 2, Rn is 0.5 plus R is 40. I have taken some weird values. Actually, consider it 4. Otherwise, that will be meaningless. 4 ohm. So, and then you can solve it of your own. So now I am moving ahead. There are 3 different cells. In fact, if there would be 2 different cells, and another one is similar to any one of any of the cells, then still we would consider that combination as different cell combination. So here what we have to do, first we have to find internal resistance which is in parallel. So Rn equal to 2 by 5, 0.4 ohm. Uh, Now there is a formula for different cells in parallel combination. E net or E equivalent upon R net equal to E1 upon R1 plus E2 upon R2 plus E3 upon R3. If there would be 4, then 4, 5, then 5, no problem with that. So En, we have to find En. Rn, we have earlier obtained. E1 is 4 upon 1. E2, 3 upon 1. E3, 2 upon 2. So it is 4 plus 3, 7 and 1, 8. En equal to 0.4 into 8. And you can find it now. And you can find potential difference also. No problem with that. But the problem comes with this. See, in the earlier question, situation was somewhat same. Here, positive and then negative, but there was a single loop. Here, positive, negative, but there are two loops. We have to supply current to this circuit, this 2 ohm resistor. So it is series because there is a single path for these cells to operate, these cells to deliver current. Here, it is not the single path. There is a division of path. So these two cells will be considered as parallel, not in series, because both together have to deliver current to this 2 ohm. So whenever there is a division in path, there are common points across which potential difference can act, and potential difference will be same here, here and here. So in such a case, remember the formula will remain same, that En upon Rn, but this greater one E1 upon R1, and it is in opposite manner, so minus E2 upon R2. So how is it so? I will briefly describe it in a separate page, but right now I am going to solve this. So okay, Rn, first we have to find Rn, 1 upon 1 plus 1 upon 0.5. Oh, this is a shortcut way. Multiply both of them, multiply it here, multiply that one that side, and then Rn will be 0.5 upon 1.5, that is 1 by 3 ohm. So En upon 1 upon 3 is equal to E1, that is 2 upon 1 and minus 1 upon 0.5. Oh god, how I have designed this question. That's amazing. 2 minus 2. I wasn't looking for this result, but net EMF is 0. So that's really surprising. You can try out this question with a different value, or I am giving you the same question. I am marking it as 3 volt, and then you can solve it and write down in the comment what is your En for that circuit.